Righto, here is a worked example in the forces section. It's a moments problem. We've got Jill and David on a seesaw. Okay, so let's have a look at the problem. A seesaw in a playground consists of a beam AB length 4 meters, which is supported by a smooth pivot at its center C. Jill has mass 25 kilograms, sits on end A. David has mass 40 and sits at a distance x meters from C, as shown in the diagram. The beam is initially modeled as a uniform rod. Using this model, find the value of x for which the seesaw can rest in equilibrium in a horizontal position. Okay, so first things first, let's draw our forces diagram. So we've modelled the beam, it's a uniform beam, so we're therefore assuming that's the mass at the centre point, the centre of the beam, and therefore the force acts downwards from that. Force of weight, is down from that point at the centre. Okay, so we've got quite a simple little model here, what we're going to do is we're going to take moments about that central point C. It does take out two of the forces, which probably cancel each other out anyway. But there's the weight of the beam, and there's the reaction at this pivot here, upward reaction. Anyway, taking this is our reference point here, and we're not worried about that at all. So what we're going to do is we're going to look at the clockwise moments and the anti-clockwise moments. So on the left, we've got the anti-clockwise moments. So basically that's the 25. Now this is Jill. She's 25 kilograms. So her the force due to her mass is 25 g, g being the acceleration due to gravity, and the distance from the reference point is 2, so it's it's 25 g times 2. Written it the other way around there, but that's what it is. And then on the other side, we've got 40 g times x, being David's weight. So we've got a little equation here in x. The g's cancel out. And if you haven't seen one of my moments videos before, I always suggest that you refrain from actually multiplying through by any value for G, usually 9.8, because you may well get this cancellation going on. Then that's what we've got here. It gives us an equation in x. We can solve that easily, and it comes to 1.25 meters. So that length is 1.25 meters. Seems completely plausible, doesn't it, when we look at the weights. State what is implied by the modelling assumption that the beam is uniform. Well, if it's uniform, the mass is in the middle. We know the fulcrum's in the middle. So if the mass is in the middle, then our simplifying our assumption anyway that we took moments about C, we're not getting any extraneous forces. If it wasn't uniform and the weight was sort of biased towards one end, then we would have to take that into consideration. But we've got no moments about the pivot for the weight. That's what we're assuming. David realizes that the beam is not uniform, after all, as he finds he must sit at a distance 1.4 from C for the seesaw to rest horizontally in equilibrium. The beam is now modelled as a non-uniform rod of mass 15 kilograms. Right, now we need to know what the mass is. Using this model, find the distance of the centre of mass of the beam from C. Okay, so this is the new diagram. And incidentally, just as a matter of practice when you're doing these things, I've always said, draw your own diagram. Don't be tempted to scroll on the one that they provide. Draw your own nice simplified diagram. In the situation like this, where the problem is changed, essentially, then draw another diagram. You then try and superimpose things on top of this diagram. It can get confusing. And the other thing is, if you want to go back and check, then if you're checking the first part of the question against the diagram that's been modified for the second question, it's going to be a bit confusing. So I would suggest you draw a second diagram and work from that. Okay, so now what we got there? Well, this basically this situation here. So this distance is we've called y. We used x in the first part, so it's a good idea to use a different letter. Y, and this distance up to where David is sitting, he discovered it's got to be 1.4. So now we can just go through and match our clockwise moments with our anti-clockwise, and we are taking moments about c again. That's what this bit of notation actually means, and an examiner will be happy with that. So clockwise, we've got 40 g times 1.4, and anti-clockwise we've got this 15g acting at a distance of y, and then this 25g acting at a distance of 2 from the center. So we've got an equation in y. Again, the g cancels out, and we've got an equation in y, and we solve that. It gives y as being 0.4 meters. Just a little footnote. Basically, because g cancels out in all this, this means that if we stage this this exercise on some other planet, or maybe on the moon somewhere where the value of g, the acceleration due to gravity, is different, then all the distances would actually be the same. So so that's an interesting little footnote, I think. Right, so that said, well, thank you for listening, and I'll see you next time.